We've been hinting at the definition of eigenvalues and eigenvectors for a while now. I haven't fully defined it yet, but I've more or less told you the idea of what it is a few times, but I haven't told you how to find it in general or given you like a standard procedure to find eigenvalues and eigenvectors for a matrix. So definition, a linear map f from V to itself has a scalar eigenvalue, which will usually be denoted with a lambda. This is a constant in R. Sometimes we allow for this constant to live in the set of complex numbers. So you can think of this as imaginary numbers, like 2 plus 5i, 5 square root of negative 1. Anyway, so a map has an eigenvalue, which is a constant, if there is a non-zero eigenvector v in the vector space, such that f of v is equal to lambda v. This is so v satisfying this condition here is what it means for a vector v to be an eigenvector. Okay, so f of v equals lambda v. That's what it means to be an eigenvector with associated eigenvalue lambda. Linear maps. So this is how we define it for linear maps. How do we define it for matrices? Well, it's more or less the same, except we're using the map f given by f of vector is equal to a times vector. A is our matrix. So matrix A has an eigenvalue of lambda with associated eigenvector v if a times v is equal to lambda v. So typically our vector v we assume to be a non-zero eigenvector because this equation is always satisfied for any scalar if v is the zero vector. So typically we are most interested in the non-zero eigenvectors v that satisfy these two equations. Okay, here's an example. So the map pi from R3 to R3 given by, it's a sort of close to projection except we scale in the first two coordinates. So x, y, z goes to 2x, 2y, 0. So what are some eigenvalues for this? So this is a really simple map, so it's a little easier to see what some eigenvalues and eigenvectors might be. So this has an eigenvalue of 2 associated to any non-zero eigenvector of the form x, y, 0. So I'm giving you an infinite collection of eigenvectors associated to this eigenvalue of 2 right here. And this is true because pi of x, y, 0 is equal to 2x, 2y, 0, right? This map just tells me make my third coordinate 0. And so I get 2x, 2y, 0, and I can factor out this 2. And now I have pi of vector is equal to 2 times that vector. So typically you'll want to, in a lot of situations, you'll want to just like pick one specific eigenvector associated to an eigenvalue. There are some situations where that's like more relevant. Sometimes you're actually interested in the entire set of eigenvalues, and it's useful to be able to find those. We'll talk about how to find those later on in this section. But anyway, that's not the only eigenvalue for this map. Lambda equals 0 is an eigenvalue. For example, the vector v equals 0, 0, 1. And this is because pi of 0, 0, 1 is equal to, so again, we just make the third coordinate 0. And now this, so the 0 vector is equal to 0 times the vector that we started with, which was 0, 0, 1. And you see that for any vector v of the form, let me get red here. If v was equal to any vector of the form 0, 0, z, then this would also be an eigenvector for the eigenvalue of the 0. You might be thinking that I made a big deal about things like not being 0. So let me go back up here. So our eigenvector, we typically don't allow to be 0 because no matter, so if v is the 0 vector, then f of the 0 vector, if f is a linear map, f of 0 is always going to be equal to lambda times 0, because this is always 0 itself. So f of 0 is always equal to scalar times 0. However, it is not always true that f of vector is equal to 0 times the vector. So this is what it means for the 0, for the scalar 0 to be an eigenvalue of a function. So if 0 is an eigenvalue, right away you see that so if 0 is an eigenvalue, then that tells you that f of vector, this has to be a non-zero vector, is equal to the 0 vector, or in the case of matrices, you would have A times V is equal to 0. And so having a 0 eigenvalue is basically the same thing as saying that the null space of your map or matrix is non-zero. Okay, anyway. So the question for the rest of this video is going to be, how do we find an eigenvalue or eigenvector for a matrix A? So let's walk through this. So let's say if lambda is an eigenvalue for, let's just say, a matrix A with eigenvector V, then so that means that AV is equal to lambda V. That's just what it means. So I can actually subtract over lambda V on both sides. And now this is equal to the 0 vector. Okay. So I have a V in both of these things. So the idea is I want to factor out the V. So this right here, as I've written, is wrong. Don't do this. What you actually, so this doesn't make sense. A minus lambda does not make sense. For this to make sense, I need to be subtracting a matrix minus another matrix of the same size. So remember, for a matrix to have eigenvalues and eigenvectors, it has to be a square matrix because it has to represent a map from a vector space V to itself. So it's square matrix. So here's what we do instead. So I have AV minus lambda V is equal to lambda times the identity matrix times V. And now A and the identity matrix have the same size, as do lambda times the identity matrix. So now I can factor and have A minus lambda times the identity matrix times V on the left side. So I have A minus lambda I times V is equal to 0. Okay. So this, what is this telling us? This is telling us that, so I have a matrix B such that BV is equal to 0. This is a true solution, and V is not equal to the 0 vector. This tells me that this matrix has to be a singular matrix. Because it has non-zero solutions to the, well, its null space is non-trivial. It has non-zero solutions to the homogeneous system of equations that it represents. So anyway, this is a singular matrix. Being singular is, so this is true if and only, if and only if the determinant is equal to 0. And so is there anything more I want to say about that? Yeah, no, this is it. So so what we really are interested in is when is the determinant of a minus lambda I equal to 0. So this is what we're going to look for our eigenvalues. And to get our eigenvectors, we just go back up to this right here. So eigenvalues are constants lambda such that the determinant of a minus lambda I is equal to 0. And then eigenvectors, v associated to lambda, are non-zero solutions to the equation a minus lambda in times v is equal to 0. So here's our general process. We find our eigenvalue by setting this determinant a minus lambda I equal to 0 and then solving for lambda that way. This will be a polynomial. I'll do an example in a minute to show you how this works out. And then once we get our possible solutions to this equation, this is one equation right here, right? Then we find our eigenvectors associated to each of the eigenvalues that we found in that process by finding all non-zero solutions, or any non-zero solutions, to this equation here, which is a matrix equation or a vector equation, whatever you want to call it. Okay. So that's our general process. So let's do an example. Here's a matrix A. Find all eigenvalues and eigenvectors. So first I want to do A minus lambda times the identity matrix and take the determinant of that. So this is the determinant of 2, 4, 0, 3 minus, so lambda times I2 looks like this. So I'm just scaling the identity matrix by a variable lambda. And now this is equal to 2 minus lambda, 4, 0, 3 minus lambda. Okay. And so this determinant, so this one's easier because this is already an upper triangular matrix. It's in echelon form, so its determinant is just the product down the diagonal. And this makes it really easy because this is like already given to us in factored form. And then so if a minus lambda I2 is equal to 0, then we see that lambda is equal to 2 or lambda is equal to 3, because one of these two factors had to be equal to 0. Okay. So now let's find eigenvectors. So eigenvectors. So let's do lambda equals 2 first. So I want to solve a minus lambda I, so lambda is equal to 2. So 2I, should be a parenthesis, times v is equal to 0. So a minus 2I is equal to, so a is equal to 2403. 2403, and then I subtract off 2 times the identity matrix. this is equal to 0, 4, 0, 1. So then if this times vector is equal to 0, this is giving me two equations here. It's telling me 0x plus 4y is equal to 0. It's telling me 0x plus 1y is equal to 0. So y, of course, has to be equal to 0. And x is free. X equals x. So eigenvectors have the form xy is equal to x 0, so the y coordinate is 0. And this is going to be all of our eigenvectors for this eigenvalue of 2. Okay. Good. So let's do lambda equals 3 next. So I'll do this one a little quicker. So a minus 3i is equal to, so it was 2, 4, 0, 3, I believe. 2, 4, 0, 3. Okay. So this is negative 1, 4, 0, 0. So if this times vector is equal to 0, then I get negative x plus 4y is equal to 0. And then my second equation is 0 is equal to 0. So I don't care about the second equation. The first equation becomes x is equal to 4y, or x is equal to, well, actually, no, this is fine. This is good enough. I'm just going to, why are you like this? Okay, there we go. All right, so eigenvectors for lambda equals 3 have the form, instead of x, I'll write 4y, and then I'll write y for the second one. So you can think of y as being our free variable here. Great. So, yeah. We could also like double check that this is right. One sec. Why are you being like this? Okay. Cool. We could also double check that this is right by just showing, I'll just do it for this one. So let's show that AV is equal to lambda V. So here I have A, and now I'll do the eigenvector 4, 1. So this is equal to, if I actually multiply this out, I get 2 times 4 plus 4 times 1. So that's 8 plus 4 is 12. And I get 0 times 4 plus 3 times 1, that's 3. I could factor out a 3 from both entries, so 3 times 4 is 12, so I get 4, and then 3 times 1 is 3. So this is equal to, so I get AV is equal to, so 3 is our lambda V. And so that's how we can check that we know that we were right. And we could have done the same thing up here. We could have just done, we could have shown that A times 1, 0 is equal to, what was our lambda? 2 times 1, 0. We could have shown the same thing. So this was 2, 4, 3, 0. And I'm pretty sure that if you work this out, it should work out. So the first entry you would have 2 plus 0, second one you'd have 0 plus 0. So we'd have 2 comma 0, which is equal to 2 times 1, 0. So that one works too. Okay, cool. That's enough of me doing things. Here's a harder example. I want you to pause the video and try to find all eigenvalues and eigenvectors for this matrix A right here. So this is going to be a little bit harder. I want you to see what problems come up when you try this. It'll be a little bit more complicated than the previous example. in particular, it'll be harder to find what your eigenvalues are for this. So pause the video, give us a shot, and then when you are done, have your answer, or you get stuck, unpause the video and we will go through this. Okay, I'm going to assume that you have had enough time to try this for yourself, and I will do this. So let's solve a minus lambda I, 3 in this case, is equal to 0. So a minus lambda I, so I get 1 minus lambda, 2, 1, 2, 0 minus lambda, negative 2, negative 1, 2, and 3 minus lambda. So that's our determinant. What is this equal to? What's the easiest way to do this? I think I'm going to expand along the first row. So I'll get 1 minus lambda times negative lambda, negative 2, 2, 3 minus lambda, minus 2 times 2, negative 1, negative 2, 3 minus lambda, and plus 1 times 2, negative lambda, negative 1, 2. Let's see, am I doing this right? This looks like that. Okay, that one's good. Second one, 2, negative 1, negative 2, 3 minus lambda, and then the third one I would have 2, negative lambda, negative 1, 2. And I am alternating the signs of these, so that looks good. All right, what's that equal to? First one is 1 minus lambda times negative lambda times 3 minus lambda minus negative 4, so that should be plus 4. Okay, then I get minus 2 times 6 minus 2 lambda, it's the first product, minus, that will be positive 2, so minus positive 2 would be still negative, and then plus 4 minus, this will be positive lambda, so I just get 4 minus lambda here. Maybe I can actually move this up. Okay, good. Let's simplify this. So, all right, this would be lambda squared minus 3 lambda plus 4, right? And then this right here would be minus 2 times negative 2 lambda plus 4 minus lambda. Okay. Let's distribute the negative lambda to everything first. Negative lambda cubed plus 3 lambda squared minus 4 lambda. Okay, and then we distribute the positive 1 to everything next. So plus lambda squared minus 3 lambda plus 4. Now I'll distribute this negative 2. So I get plus 4 lambda minus 8 plus 4 minus lambda. Okay, let's combine like terms. Negative lambda cubed, that's the only cubic term here. Squares, so I get 3 lambda squared plus 1 lambda squared, so that's plus 4 lambda squared. Right. Negative 4 lambda minus 3 lambda plus 4 lambda minus lambda. So I get a negative 4 and a positive 4 cancel out. And then I'm left with negative 3 minus 1 lambda. So this is equal to negative 4 lambda. Okay. And then constants. There's a 4, there's a -8, there's a 4. Those add up to 0, and so that makes our lives a lot easier for the next stage because it's going to be a lot easier to factor now. So now I can factor out a lambda from all this because I just have a 0 right there. And this is equal to lambda times, well, I'll just say negative lambda times lambda squared plus, nope, that'd be negative lambda squared minus 4 lambda plus 4. And I can fact this as lambda minus 2 squared. Okay, so solutions to setting this equal to 0 tells us that lambda is equal to 0 or positive 2. And note that there is a power of 2 here. This is going to be somewhat relevant later on. So anyway, let's now find all of our eigenvectors associated to these eigenvalues. So lambda equals 0. So here I'm really just solving a minus... So I'm solving a minus 0I times vector is equal to 0. So I'm really just solving for the null space of our matrix A in this case. Okay, what is A? Let's copy A. Let's copy A down over here. Copy that. So let's find the null space of A. That's going to give us our eigenvectors for lambda equals 2. Okay. I'm going to do -2, row 1 plus row 2 and replace, and I'm going to do row 1 plus row 3 and replace. -2, okay. So I get -2 times row 1 plus row 2, that'll be -4. -2 minus 2, that's also -4. Okay, and now that's easy. That's going to be a 0. 2 plus 2 is 4. 1 plus 3 is 4. Okay, cool. And right away I can see that I can add row 2 to row 3 and replace. Okay. And then I'll divide row 2 by -1/4. Sorry, I'll multiply by -1/4. And then I will do -2, row 2. Why am I doing this here? I'll do -2, row 2, added to row 1. 1, 0. 0, 1, 0, 1, 0, and this should be -1. So I get x minus z equals 0, and I get y plus z is equal to 0. And so z is going to be our free variable here. And so our solutions are going to have the form, so eigenvectors are going to have the form x, y, z equals, so x is equal to z, y is equal to -z, and z is equal to itself. And these are just multiples of 1, -1, 1. And so those are our eigenvectors for that eigenvalue. Okay. And now let's do it for lambda equals 2. Okay. So this is our matrix A. So this is for lambda equals 2. Is that right? Lambda equals 2. Just making sure we're right. Okay. So this is equal to 1 minus 1. This is now 0 minus 2. And then 3 minus 1. 3 minus 2 is 1. Everything else stays the same. Okay. Now I'll do, okay, so row 1 and row 3 are exactly the same. So I'm going to do 2 row 1 added to row 2, and then negative row 1 added to row 3 to make that a 0, a row of zeros. It's 0, negative 1, 2, 1. Okay, so 2 times 2 is 4. 4 minus 2 is 2. 2 times 2 is that. 2 times 1 is 2. Add that to negative 2 and I get 0. Okay. 2 times, right? Yeah, and adding 4 to negative 2. Okay. And then I can just do negative row 2 added to row 1 and replace. I get negative 1, 0, 1, 0, 2, 0, 0, 0, 0. Okay, and I'm just going to go ahead and I'm going to say negative x plus z is equal to 0, and then 2y is equal to 0. So y is equal to 0, and then x is equal to z, and z is going to be free. So then eigenvectors have the form x, y, z, where x is equal to z, y is equal to 0, and z is equal to itself. And these are just multiples of 1, 0, 1. And again, you could check that this is right by showing a times vector is equal to lambda is equal to 2, right? 2 times vector. So is this true? Is this a true statement? I want to be sure that this is right and be confident in this, so why not? We're already here, so 1 times that's negative 1 plus 0 plus 1. Negative 1. Oh no. This is a 0. Okay. And I copied the wrong thing. So actually what I wanted to do was this matrix A because what I had actually done is A minus 2 times the identity matrix, which of course this would give me is equal to the 0 vector if I do this. All right, now this should be right. So 1 times 1 is 1, plus 0 plus 1, that's 2. Next entry should be 0. 2 plus 0 minus 2, so 2 minus 2. And then negative 1 plus 0 plus 3. Negative 1 plus 3 is 2, and this is equal to 2 times 1, 0, 1. So this works.